We are going to be talking about potentials today. Electrical potential transmits signals at the neuron's plasma membrane. These signals occur due to the concentration of the charged particles between the ECF and the ICF. Inside and outside of the neuron, the charged particles are sodium ions, potassium, and cellular proteins. The fluid in the ECF is significantly positively charged, and the ICF is more negatively charged. Because of the different charges, electrical potentials occurred at the plasma membrane. Resting potential occurs in the ICF where it is more negative than the ECF. The ICF measured value is negative 70 millivolts compared to the ECF. A neuron at rest is negatively charged. The inside of a cell is in a polarized state at approximately negative 70 millivolts more negative than the outside. The sodium and potassium pumps are using ATP to transport sodium ions out of the ICF and potassium ions into the ICF. The potassium ions in the ICF area with negatively charged proteins will help set up with the resting membrane of negative 70 millivolts in the ICF. The membrane is now at a polarized state. Even though the sodium and potassium pumps are constantly using ATP to maintain a resting potential in the plasma membrane to send electrical signals, the ions still need to be diffused through the membrane to produce currents down the length of the membrane. These currents cause disturbances to the membrane's polarized state by various kinds of stimulation, such as chemical, light, temperature changes, and pressure. Local potentials, changes in membrane potential of a neuron depending where the stimulation occurs. Different neurons can be stimulated by certain things. For example, a chemical disturbance can cause changes to occur. They are graded, which means vary in magnitude with stimulus strength. Stronger stimuli will open more sodium gates. It is decremental, which gets weaker the further they spread from the point of stimulation. They're reversible. If stimulation stops, the cell quickly returns to its resting membrane potential. When the dendroid in stimulation, the sodium gates will open, allowing sodium ions to flow through to the ICF. The positive sodium will cause the negative 70 millivolt resting potential to become more positive. This will lead to depolarization. The positive sodium ion entry results in a current that travels through the plasma membrane of the soma and possibly to the axon hillock. This short-range change in voltage is called a local potential. Action potential causes a more dramatic change in the polarity and membrane potential compared to local potentials. Occurrences at the axon hillock and along the axon's length. It follows the all or none law, which occurs at full strength or not at all. Action potentials are not graded. They're also non-decremental, which maintains a strong strength down the entire axon length. It is irreversible, which once it starts, it cannot be stopped. For an action potential to occur, the local potential has to reach the axon hillock and depolarize the resting membrane at negative 70 millivolts. Local potential has to be strong enough to cause some of the sodium gates to open and reach a threshold of creating an action of negative 55 millivolts within the ICF. The value of the ICF may increase from negative 55 millivolts up to positive 35 millivolts, which is the peak value of the action potential. The sodium gates will close and allow potassium gates to open, causing potassium ions to diffuse out into the ECF, shifting the voltage back to negative values. Once the potassium ions diffuse out into the ICF returns to negative 70 millivolts. The potassium gates will close. When both the sodium and potassium gates close, the membrane has reached a polarized state and resting potential has been re-established.